Okay, today's starter. I'm going to give you a mass spring simple harmonic oscillator, and the mass is given to be 300 grams, and a frequency of 1.85 hertz. What is the angular frequency? What is the period? What is the spring constant? And if the maximum speed is 2.0 meters per second, what is the amplitude going to be? So here's, I kind of wrote it up. So this mass is equal to 0.300 kilograms. I'm already trying to change everything. And the frequency is equal to 1.85 hertz. And then find. What are we trying to find? Well, for A, we want angular frequency. That's omega. And then B, what is the period? And then C, what is the spring constant? That's lowercase k. And then D, what is the, if the maximum speed is 2 meters per second, so that's right in the middle there, right? V equals 2.0 meters per second. Find the amplitude. Okay, so let's solve. And then part A, well, the angular frequency is in radians per second, and regular frequency is in full cycles per second. So I'm going to write this down, 1.85 cycles or oscillations, however you want to think of it. If it's a wheel spinning, it's rotations. It all kind of works the same way. 1.85 cycles per second. And then one cycle is 2 pi radians. Remember, one cycle is when the motion starts to repeat itself. And if you were to plot the position as a function of time, it would make a sinusoidal wave. And so, using radians makes sense. And so I'll get my calculator. So that's 1.85 times 2 times pi equals, and I get 11.6 radians per second. And that's equal to omega. Now part B, there's a couple ways to do this, but based on what's given, the period is just 1 over the frequency. So that's 1 over 1.85 cycles or oscillations per second. So 1.85, take the reciprocal of that. And so the period of this oscillation is going to be 0.54 seconds per cycle. I'm just going to call it seconds. But it takes 0.54 seconds to go through one complete cycle of the oscillator. Okay, that makes sense to everybody? Hopefully these two were quite easy. Now for part C, well, I always forget, is it M over K or K over M? And you can use the units to figure it out, but here's what I like to do. I like to say, well, the force of the spring is the force that the spring applies is the net force, and the net force is equal to MA, and MA is equal to negative KX. So acceleration, you divide by M, you divide by M, and we know that this right here is omega squared. At least that's what I memorized. So we know that omega squared is equal to K over M. And so now I can solve for K. K is equal to omega squared times the mass. And so, how am I doing? Yeah, good. So we got omega squared, we have 11.6 radians per second. We're going to square that and then times the mass. And the mass is given to be 0.3 kilograms. And so when I go through the arithmetic, I get 40.4. Now let's take a look at units. This is kilograms per second squared. What the heck? But really it should be newtons per, remember the spring constant is how much force you need to stretch at 1 meter. So let's check the units. That's newtons per meter. And a newton is a kilogram meter per second squared. And then we're going to divide that by meters. And the meters can, I get kilograms per second squared. So that's good. So I can say the spring constant is equal to 40.4 newtons per meter. If you left it as kilograms per second squared, that's not wrong. Okay, let's see if I can fit part D here in the bottom of the paper. Well, what I'm going to use here is that I'm going to use energy. And I'm going to say that the mechanical energy in the middle, I'll call it E1, is equal to the elastic potential energy at the maximum position. So this is going to be 1/2 the mass times our speed squared. And that's going to be that's going to be equal to the energy stored in the spring when it's at its amplitude. And that's 1/2 Ka squared. So we can get rid of the 1/2. We can solve for A. Now, A is going to be equal to m over K. Times the velocity squared. And then you have to take the square root of the whole thing. Now, m over K, isn't that the angular velocity? Yeah, if I, let's see. Oh, yeah. So, well, let's just plug in the values and then we'll go over that other thing. So m is given to be 0.300 kilograms divided by K, which we calculated to be 40.4 newtons per meter. And then we're going to take that and multiply it by the velocity, which is given to be 2.0 meters per second. And I'm running out of room here, so let me put it over here. So A is equal to, let's see, 0.3 divided by 40.4. That equals the small number. And then I'm going to take the square root of that. And then I'm going to multiply that times 2. And I get 0.17 meters, or I'll put 172 meters, or 17.2 centimeters. You want to put it in centimeters. That's what I got. Anybody else get the same thing? Did you get it a different way though?
Yeah.
What'd you do?
I just used Vmax equals A times, or the amplitude times omega.
Yeah. And that's kind of what I was thinking after I got this. I went, well, oh, wait a minute. That's right. This is, yeah, the maximum velocity is equal to the angular frequency times the amplitude. And so you can solve for the amplitude by saying that's the maximum velocity divided by omega. And that's going to be 2.0 meters per second divided by, what do we get for omega? 11.6 radians per second. And so that's 2 divided by 11.6 equals, and yeah, you get the same answer. Of course you would. But it all works. It's all consistent. It all makes sense within itself. Okay. Let me, yeah, I'm already zoomed out. Okay, so any questions on all these little things? Okay, that is all.